Today, we're really getting under the hood of time series analysis. We often talk about cleaning data, removing trends, dealing with seasonality to get it stationary. But what about what's left? When the series is stationary, but values still depend on past values, that autocorrelation, that internal memory.
That's the core of it.
We need a language, a framework to model that remaining structure. Okay, let's unpack this. Our mission for you, the listener, is to get comfortable with the fundamental building blocks of autoregressive moving average models, ARMA.
Exactly, because once you have that stationary series, ARMA models are really your go-to toolkit. We'll break down the main types, the autoregressive or ARP, the moving average, MAPR, and then how they combine into ARMA.
So understanding the theory behind them, and importantly, how to tell which one fits.
Precisely. How to diagnose your data. Right.
Yeah.
So it all starts with stationarity, specifically weak stationary. Think of it like consistency over time. Two main things need to hold. The average value, the mean, must be constant.
Doesn't drift up or down.
Correct. And second, the relationship between data points, the autocovariance, should only depend on how far apart they are in time, the lag age, not when they occurred.
So the connection between today and yesterday should be the same strength as the connection between, say, a week ago and the day before that. The actual date doesn't matter, just the time gap.
You've got it. That's the essence. And our baseline for this is pure white noise.
Ah, the perfectly random process?
Exactly. It's the ideal stationary series. Mean is 0. Autocovariance is 0 everywhere except at lag 0, where it's just the variance, no memory at all.
Okay, so that's the ideal. Now, what about a classic non-stationary example, like a random walk?
Right, the random walk, where today's just yesterday, plus some random shock. Think stock prices, maybe.
Why is that one non-stationary? It feels like it should have memory.
It does, but it's an unstable memory. Its variance actually grows with time. The autocovariance depends explicitly on T, which violates our second rule. Basically, the effect of a shock way back in the beginning never really fades away. And if you plot the autocorrelation function, the ACF,
the diagnostic plot.
Yeah. For a random walk, you'll see the correlations decay incredibly slowly. Often looks like a straight line sloping down. That slow decay is a huge red flag for non-stationarity.
So you absolutely have to difference that kind of series first. Get rid of the trend or the walk.
Before you can even think about ARMA modeling, yes.
All right, so let's say we've done that. We have a nice stationary series. Now we model the memory. First up, autoregressive. This sounds like it's about the series regressing on itself.
That's a good way to put it. It's about behavioral memory. The current value is modeled as a linear combination of its own previous p-values plus a new random shock, epsilon.
Here's where it gets really interesting. You mentioned stability. If it depends on its past, how do we ensure it doesn't just explode or oscillate wildly forever?
Yes, the stability condition. It's crucial. For an AR process to be stationary and stable, there's a mathematical requirement involving its characteristic polynomial.
Okay. Complex math alert.
A little, but the concept is key. All the roots of this polynomial must lie outside the unit circle in the complex plane.
Right.
What that means practically is that the influence of past values eventually dies out. It prevents infinite memory. For the simplest case, the rule is very simple. The absolute value of that coefficient be less than 1.
If less than 1, it's stable.
Correct. If it equals 1.
Or back to a random walk, non-stationary.
Exactly. So that boundary is critical.
Okay, so AR is direct dependence on past values, need stability. If I suspect my data works like this, how do the charts, the ACF, heap ACF, tell me the order?
This is where visual diagnostics really shine, especially for pure AR models. We need both the ACF and the PACF.
Autocorrelation function and partial autocorrelation function.
Right. In an AR process, correlation isn't direct.
It ripples through.
Kind of, yeah.
Yeah.
So the ACF doesn't just stop, it damps out. It decays towards 0, sometimes smoothly, sometimes oscillating positive and negative if a coefficient is negative, but it fades gradually. We call it mixed exponential decay.
Okay, so ACF decays for AR. What about the PCF?
The PCF is the hero here for AR models. It measures the direct correlation after removing the correlation that's explained by the lags in between.
It isolates the direct link.
Precisely. And since an AR model only directly depends on the first P lags.
And the PCF should be 0 after lag P.
Exactly. It cuts off abruptly. You'll see significant bars for lags 1 through P, and then suddenly nothing significant after that. That sharp cutoff in the PCF is the classic signature of an AR process.
All right, AR is about past values, PCF cuts off. Now the other side of the coin, moving average, MA. What's the focus here?
Here, the focus shifts from past values to past errors or shocks. Think of it as shock memory. The errors is modeled as dependent on the current random shock, epsilon, and the previous Q shocks, epsilon 1, epsilon Q.
So it remembers unexpected events from the recent past, not necessarily the overall level of the series.
That's a good conceptual way to see it. And a key difference is that MA models have a strictly finite memory. The influence of a shock, say epsilon Q, completely vanishes after Q periods.
So they're always stationary, no complex stability conditions like AR.
Correct. Since they're just a finite weighted sum of white noise terms, which are stationary, the MA process itself is always stationary. Much simpler in that regard.
Okay, simpler structure, finite memory based on past shocks. How does this model show up in the ACF and PACF plots? Is it the reverse of AR?
It is precisely the reverse.
Yes.
Because it only depends on shocks up to epsilon Q if you calculate the covariance where the lag H is greater than Q.
Which means the ACF cuts off.
Bingo. The ACF provides the sharp signal for an MAQ process. It will have non-zero values up to lag Q and then drop abruptly to zero within the significance bounds for all lags beyond Q.
So ACF cutoff means MA. What about its PCF then? Does that decay?
Yes. Behaves like the ACF for an AR process. It doesn't cut off. It damps out.
Why is that?
It stems from the fact that any finite MA process can be mathematically inverted into an infinite AR representation. So while the direct dependence on shocks is finite, the implied dependence on past values technically extends infinitely far back, just with rapidly diminishing importance.
Wow, okay. That's quite symmetric then. Let me try to summarize. AR. Memory of past values. PACF cuts off at P. ACF decays. Memory of past shocks. ACF cuts off at Q. PACF decays.
That's the perfect theoretical distinction for the pure models.
Okay, pure AR, pure MA.
Yeah.
But reality is messy, right? Often it's a mix.
Very often. That leads us to the general autoregressive moving average, or ARMA model. It combines both aspects.
So metonymy depends on its own past P values and the past Q shocks. Best of both worlds.
Potentially, yes. It's a very flexible class of models, but it makes reading those ACF and PCF plots much harder.
Uh-oh. Why? No more cutoffs.
Exactly. Because both the AR and MA components are active and interacting, neither the ACF nor the PACF typically exhibits a clean cutoff.
So they both just decay.
They both tend to damp out, exhibiting complex patterns of mixed exponential decay. The AR part influences the decay pattern of the ACF, and the MA part influences the decay pattern of the PACF. Visual inspection becomes, well, much less definitive.
Right. So if I see both plots just sort of tailing off, I might suspect an ARMA model, but figuring out the P and Q just by looking seems difficult.
Difficult is an understatement. It's often practically impossible, especially for higher orders.
So what do we do? How do we choose P and Q in practice for ARMA models?
This is where we lean heavily on a more quantitative, structured approach. It generally involves 3 stages: estimation, selection, and validation.
Okay. Break those down. Estimation.
First, based on maybe some tentative guesses from the plots, you'd propose a few candidate ARMA models. Then you need to estimate the actual coefficients for each candidate model using your data.
How are those estimated?
There are several methods. Common ones include Yule-Walker equations, which are based on the sample ACF. There's also the Berg method. But perhaps the most widely used, especially with modern software, is maximum likelihood estimation, MLE.
MLE. That often assumes normality of the errors, right?
Typically, yes. Yule-Walker is computationally simpler, but MLE is often considered more efficient, potentially giving better estimates if the model assumptions hold.
Okay, so we estimate coefficients for several plausible models, then selection.
Right. Now you need to compare these fitted models. How do you pick the best one? We use information criteria. The most common are the Akaike Information Criterion, AIC, and the Bayesian Information Criterion, BIC.
Ah, AIC and BIC. I've seen those. They balance model fit with complexity.
Exactly.
Yeah.
Both AIC and BIC penalize models that don't fit the data well, but they also penalize models that use too many parameters that have high P or Q. They trade off goodness of fit against model parsimony.
Parsimony meaning simplicity.
Simplicity, yes. We generally prefer simpler models if they fit reasonably well. An important point is that BIC tends to penalize complexity more harshly than AIC.
So BIC might lead you to choose smaller P and Q values than AIC would.
Often, yes. BIC tends to favor more parsimonious models.
Okay, estimate, then use AIC or BIC to select the best candidate orders. What's the last step?
Validation. And this is absolutely non-negotiable. You've chosen a model, say ARMA, ROS1, had the lowest BIC. Now you must check if that model is adequate. You look at the residuals. The residuals are the errors the model makes.
What should the residuals look like?
Ideally, they should look like white noise.
Ah, back to the beginning. No structure left.
Exactly. They should be essentially uncorrelated. You'd use statistical tests like the Jung box test to check for any remaining autocorrelation in the residuals. They should also, ideally, have constant variance, homoscedasticity, and be normally distributed, though the uncorrelatedness is the most critical part.
And if the residuals fail these tests, if there's still pattern left in the errors,
then your chosen model is misspecified. It hasn't captured all the dependent structure in the data. You have to go back, reconsider your candidate models, maybe try different P's and Q's, and repeat the estimation, selection, and validation process.
It's an iterative process then.
Very much so.
Okay, so let's pull this together. Theoretically, the pure models give clear signals. AR means PACF cuts off. MA means ACF cuts off. Behavioral memory versus shock memory. But for the combined ARMA model, both plots usually decay, and we have to rely on this quantitative cycle. Estimate possibilities, use AIC or BIC to compare them, and critically validate the residuals of the winner.
That's the practical workflow. It's a synthesis. You start with the visual clues to get a rough idea, then refine using the quantitative tools, the information criteria, and, most importantly, the diagnostic checks on the residuals. You're looking for the simplest model that adequately turns your data's residuals into white noise.
Right. Now, you mentioned different estimation methods like Yule-Walker versus maximum likelihood can give different coefficient estimates.
They can, yes.
And that BIC specifically pushes towards simpler models. It raises a final thought for our listeners to chew on. How much weight should you, as a practitioner, put on that mathematical elegance or parsimony that BIC prefers versus maybe finding a slightly more complex model that, while penalized by BIC, actually gives you better forecast accuracy when you test it on data it hasn't seen before?
The classic bias variance trade-off in a time series context.
Exactly. That tension between theoretical simplicity and raw predictive power on new data, that's something you'll likely wrestle with every time you build a time series model.